When you look at the bleeding edge of modern technology, rendering the massive open worlds of AAA games, or training colossal AI models in PyTorch, you are looking at immense computational strain. The exact same strain applies to global financial markets. To execute millions of transactions per second flawlessly, volume of data, they all rely on the exact same underlying architecture. Managing the data demands of the modern world requires a specialized foundation, a language engineered specifically to operate at the absolute limits of physical hardware. To understand why this language exists, we have to go back to 1980. A Danish researcher named Bjarne Stroustrup was starting a side project at Bell Labs. Programmers at the time were trapped by physical hardware limitations, forcing them to choose between two highly flawed extremes. Look at the scale. The C language hit maximum on the speed metric, lightning fast but structurally empty, lacking organization for complex applications. On the other end, Simula filled that gap using object-oriented programming, but its speed was flat. Executing programs was agonizingly slow. You couldn't build complex, fast software with either option alone. True technological progress required engineering a hybrid, a tool with the raw horsepower of C and the architectural brilliance of Simula. By 1983, that hybrid side project was actively functioning. Stroustrup initially called his creation New C, or simply C with classes, but a colleague gave it the final name that stuck, C++. The ++ is a direct reference to the programming increment operator, meaning to mathematically add 1 to a value. In this visual equation, we can see exactly why it is not called ++C. You must establish the solid base layer of C first. Now, only after that foundation is set can the increment operator drop in, adding the advanced object-oriented features on top. That specific sequence gave developers exactly what they needed. The structural layer expands outward to support massive systems, while the underlying C anchor maintains the raw machine speed. The name itself is an inside joke that perfectly describes the language's core function, an evolutionary structural upgrade applied directly to a necessary foundation. Fast forward to 1998, and the language hit its first major growing pain with the introduction of the Standard Template Library, or STL. The initial reaction from programmers was largely negative. Many resisted the STL out of fear that these new templates would inject unnecessary complexity into their code. But as they began to adopt it, they realized the STL allowed for deep code reuse. Overcoming that initial resistance unlocked massive new efficiencies across the industry. Then came the late 2000s. Highly popular, user-friendly languages like Java were rapidly gaining ground, posing a very real threat of rendering older languages obsolete. The response was the C++ 11 update. By introducing modern features like multi-threading for parallel processing and the auto keyword to dramatically slash syntactical clutter, the language quickly adapted to the times. C++ did not survive decades by remaining a static relic. It survived by ruthlessly absorbing modern computing concepts while fiercely protecting its core processing speed. Today, running on the modern C++ 23 standard, this hybrid approach quietly dominates the tech stack. You will find it deep within the operating systems we rely on daily. From the massive deployment of Windows 95 to modern Linux distributions, it plays a critical, hidden role in managing hardware resources. It is the engine rendering major web browsers. It forms the framework for cybersecurity protocols like OpenSSL, and it structures massive database management systems like MySQL. And those bleeding-edge machine learning libraries we mentioned earlier, they rely entirely on C++ to handle the heavy computational lifting beneath the surface. Whenever a piece of technology hits the absolute physical limits of what the hardware can handle, this specific hybrid language remains the only logical choice to bridge the gap. It is common for new developers to look at C++ and feel intimidated. The syntax can look complex, and it often gets an unfair reputation for being outdated. But learning it means looking past the syntax. It is about gaining the power to manipulate the deepest logic of the digital landscape, giving you precise structural control over memory and hardware. Because this language manages the most critical bottlenecks in the industry, from the operating system to the AI model, it remains a standard for high-performance engineering. Mastering it shifts a developer from simply using software to building the systems that the rest of the world relies on.